talking about Rydberg blockade and things we've thought about and some preliminary experiments on trying to do quantum manipulation with ensembles of atoms. We've heard a lot of these ideas already this morning, and I'm going to review some of the requirements if we want to make high fidelity quantum manipulations, requirements on the Rydberg interactions, and talk about how that shows up, those interactions show up in various imperfections, dephasing, and how blockade protects against dephasing, and also the relationship between these requirements for high fidelity quantum manipulations and observation of suppression effects. And then finally, we'll talk a little bit about first experiments done with Mark Safman on single atom loading, deterministic single atom loading. We haven't achieved that yet, but I'll tell you about our progress towards that. So a lot of my work in Rydberg physics is done in collaboration with Mark, and Mark is going to be telling about the experiments with two individual atoms at 10 micron scale separations in his talk tomorrow, and I'll be talking about other things here in this talk. So we're all familiar with this basic idea, now 10 years old, the point of the interactions between Rydberg atoms being sufficiently strong that if you excite one atom to a Rydberg level, the excitation of a second one becomes energetically forbidden by the dipole-dipole shift. And again, there are many ways that this interaction can occur. One of the important ones is this Foerster process, where you have the possibility that two NS atoms is nearly degenerate with N-1p and Np. And that degeneracy lets there be an effective dipole moment of the system that gives rise to 1 over distance cube interaction. It's unplugged. No wonder it's not working.
Well, it's just not on the. There it is. Yeah. Sorry about that.
Okay, and in real life, these interactions are not quite resonant, and so that gives us the van der Waals dipole-dipole interaction. Nevertheless, small delta E's can make these interactions quite strong. And then short time later, Misha and others proposed extending this idea to mesoscopic systems, where we have a collection of atoms that are confined in a small enough size sample that the excitation of one of those atoms will blockade the excitation of any of the others in the sample. And so this was pointed out to be a really interesting possible system for doing quantum manipulations of this, because effectively, due to blockade, you have a two-level system with the square root of n enhancement of the Rabi frequency that we've already heard about. So some of the features of the blockade that, again, have been mentioned already several times this morning. The blockade only involves the internal degrees of freedom. You don't have to control the external degrees of freedom precisely to get it to work. The strength of the dipole-dipole interaction in most cases does not need to be precisely controlled. Again, a very attractive feature of it. Speed is almost a necessity because of many of the other processes that we'll be hearing about at the workshop. It's difficult to keep Rydberg atoms excited without them doing things like having inelastic processes of various sorts going on. And so you're almost forced to do everything fast. And I get in trouble for saying this last one. It's only really approximation, but when the blockade works really well, the atoms actually end up not experiencing forces between each other, because if it's working well, then you never actually have more than one atom in the Rydberg state at a time. So one of the important problems toward making a quantum processor using Rydberg atoms is the need to put one atom in each of a large number of sites. And as an example of what you can do with ensemble Rydberg effects, there's a nice protocol for putting deterministically loading atoms into these single atoms into these individual sites. You start off with n atoms in one site. You put them all in one hyperfine level. You use a Rydberg interaction to transfer one of those atoms to a different hyperfine level, and then eject the n-1 atoms. And at the end of my talk, I'll be showing you our first attempts to actually do that. So if you want this kind of thing to work, it's important to think about what are the constraints. Here is an energy level diagram for 3 atoms. I imagine them being in a line. And so the ground state of the system is 3 atoms in the ground state. Then you have the symmetrically excited state there. And then the whole point of the blockade is that this particular state, which is directly coupled to the ground state, is off resonant with all the possible interactions, excitations from it. So the excitation to this EGE state is off resonant by this delta 1,3 or delta 2,3. And so you get an effective 2-level system, again, with the square root of n enhancement in the Rabi frequency. Now, a very important feature of this is that if you have errors, potential errors, let's say of exciting 3 atoms, the blockade is effectively protecting you against those kind of problems. So it's now known that it's possible to have situations where 3 atoms in the Rydberg state, instead of having this delta 1, 2, 3, well, delta 1, 2, 3 could be 0. If that happens, nevertheless, the blockade is still only allows you to access that resonant state by a 2-photon off-resonant excitation. So the blockade still protects against these kind of errors. And similarly, if you have ionization, potential ionization processes or other inelastic processes, these things are suppressed for a well-blockaded sample. As soon as you have a larger sample where you have many blockade volumes, then these other things can happen, and the blockade doesn't necessarily protect you against them. An important feature of the blockade shift is in just asking, okay, how big are the errors? And the interactions show up as this blockade shift parameter we call B, which is an average of the inverse of the square of the interactions between the atoms. So the point is that if you have a range of interactions between atoms in the sample, or their various internal states of the atoms that have weak interactions, then you get preferential excitation of those. And so figure of merit for a quantum manipulation is basically what is the weakest possible interaction between 2 Rydberg atoms in your sample. And that means the long-range characteristics of the interactions are extremely important. And in addition, when you have degeneracies due to angular momentum or whatever, if you may have very strong interactions on most of your potential curves, but if you have a weak one, that can basically short circuit the blockade. And so here's I think a particularly interesting example. There's this case in rubidium 43D plus 43D is only 6 or 7 megahertz out of resonance with 41P plus 45F. And so that gives very strong van der Waals interactions for most of the internal states of the atoms. However, there's a particular linear combination of the Zeeman levels which has extremely small dipole-dipole shifts. And so even though you may have megahertz type interactions for most of the potential curves, if you actually calculate the blockade shift for a 10 micron cloud on this transition, it's only 30 kilohertz. So it's, as far as a quantum manipulation is concerned, actually a fairly weak situation. Now you can break these degeneracies with magnetic fields and fine structure effects, and that's what we've done to do these experiments with single atoms 10 microns apart using 79D or 100D kind of levels. You can apply magnetic fields and get rid of a lot of this. Okay, another interesting possibility using Rydberg physics we just heard about is making deterministic single photon sources. Very simple, conceptually simple way of doing that is to set up a four-wave mixing kind of geometry, do two-photon excitation to a Rydberg level, then stimulated emission back down, and then look at the spontaneously emitted or nonlinearly mixed photon that is produced. And the basic idea is that because of the blockade, the wave function for the excitation has the phases of these three light waves imprinted on it. And so it's like you've produced a grading in your wave function. And if you ask just what's the probability of emission into some direction, you have to sum the amplitudes, and you have a phase matching factor, just like in classical four-wave mixing. And you give an n-fold enhancement in the phase match direction. So here's a simulation of 50 atoms all confined in one blockade volume. So this kind of thing is potentially very interesting, directed deterministic single photon source. So we haven't done that, but we're starting to do some of the things that you need to realize something like that. And so I'm going to tell you about some experiments where we do two-photon excitation up to a Rydberg level, and then our third photon is stimulated emission from the Rydberg level to 6p level, and then we detect that anything is going on by looking at the spontaneously decayed 420 nanometer photons. And so instead of detecting the Rydberg atoms by field ionization, we have this very state selective method where basically these 420 nanometer photons reflect the population of the Rydberg level. And so we've seen four-wave mixing in a MOT and measured some of its properties. One of the interesting things that shows up is actually fairly large line widths, even for relatively low quantum numbers. And again, back to my connecting to my introduction here, I think a lot of the explanation for this is that we're actually weakly blockaded, and so the Rydberg interactions are actually quite important here because we're not protecting ourselves against multiple excitations in this experiment. Another example of that comes from the quantum computing effort with Mark, and that is here we're looking at coherent Rabi flopping to the 43D state. And what we've allowed to happen, instead of measuring the number of atoms, we're letting there be basically a random number of atoms with a mean of 0.3, 1.7, or 8 atoms. 0.3 atoms, we see fairly good Rabi oscillations. Even 1.7 atoms, we see substantial degrading of the Rabi oscillations, and by the time there are 8 atoms in the cloud, those Rabi oscillations are completely gone. And again, this is a situation where the blockade shift is only 30 kilohertz, even though the interactions between the atoms are strong. So the strong interactions are showing up as the rapid dephasing. But as far as a blockade type situation, this doesn't work. You've got to do something else to make blockade work in this kind of a sample. Just another example of this. This is fairly old data before we did very good Rabi flopping. But this we're down here at 28D. So the blockade shift is much less than a kilohertz, and yet even here's 11 atoms. The Rabi flopping oscillations are just completely gone. So effectively, there's very strong interactions, and you can see that basically here, even at n equal 28. Okay, there's very little interaction out at 5-10 microns, but that quickly transitions to very strong interactions at 3.5 microns. And so the point is that some fraction of the time the atoms in your trap are within this distance, a fairly substantial fraction of the time, and when they are, they basically completely dephase the excitation. And you can, other people have worked on this as well. You can make simple models of this and see how that works. So the point I'm trying to make, blockade is really sensitive to the weakest interactions in the system, dephasing to the strongest. Similarly, with suppression type experiments, again, we have possible situations where you have non-interacting states, yet you still see suppression. I'm going to show an example of that here in just a minute. So if you have these kind of non-interacting states, they encourage double atom excitations, but you're still, on average, reducing the excitation by a substantial amount. So from a quantum excitation, quantum manipulation perspective, you may have poor blockade, but you can still get a dramatic suppression of the excitation. So an experiment that we've done working on this is to do our four-way mixing in a crossed beam geometry. So this is the 780 laser here, 480 laser here to define a relatively small excitation volume. In addition here, we've made the intensity of the red beam strong enough so that we have quite substantial AC Stark shifts of the two photon resonance. And then what we do is tune the blue laser so that we are basically exciting atoms that are only sitting at the bottom of this set of the 780 laser beam. So that basically is a way to spectrally as well as spatially localize our atoms. And then we can do experiments similar to what a FAO group has done as far as measuring the number of atoms as a function of time. We have excitation transients and then also de-excitation transients from our stimulated emission. And so these kind of curves allow us to deduce what the effective average excitation and de-excitation rates are. And then what we were doing is turning on and off interactions between the atoms by adding resonant microwaves. So we couple our NS state to an NP state with microwave horn, a few milliwatts at a meter works fine because of the huge dipole moments. And so you clearly see the Outler-Town splittings in the spectra. Now the wave functions for the Rydberg states are superpositions of the S and P. You have a mixture of opposite angular momenta, or angular momenta that are different by 1, and so you get a first-order dipole-dipole interaction. Now the interesting thing is when you couple the S to a P1/2 state, and you calculate what the dipole-dipole interactions are, there were some surprises for me. So you get 4 curves, only some of which are very visible on this projector, but here's one of them. you get this angular distribution, which isn't too surprising. You get a second state, which is isotropic and has a fairly strong interaction. And then you have one state, one linear combination of the Zeeman levels, which has 0 dipole-dipole interaction in first order. So this is a situation where we can turn on for most of the potentials in the system, we have a very strong interaction. We have one that is very weak. And so we can ask, does this obey the usual scaling laws? In our experiment, the blockade condition is determined by the laser line widths of a few megahertz. And so the blockade condition is determined by basically the number, when the dipole-dipole interaction is equal to that line width. And so we can calculate the expected number of excitation sites. And also, because we have stimulated emission going on as well, the actual number of Rydberg atoms depends on a competition between our potentially blockaded excitation and our de-excitation. And so we can look at the density and intensity dependences. And so if we look at the density dependence of this with no microwaves, it's basically linear, showing that we're low enough. We're at 45 so that for our densities, really not very strong blockade. We turn on the microwaves and see a clear saturation effect as we increase the atom density. And the fits to this give us a effective interaction, which is within error bars the same, but a little bit smaller than we expected. Similarly, we can look at the intensity dependence of the 480 nanometer light with and without the microwaves. With the microwaves, you still get kind of a saturation of effect because of the stimulated emission going on. When we turn on the microwaves, then we get a nice saturation. Again, the point that I'm trying to make here is that this is a situation where there is a state in which we can excite pairs of atoms with essentially no interaction, and still you get the kind of expected scaling laws, and that's because these kinds of experiments are looking for a change in the excitation, aren't sensitive to the weak potentials in the way that true blockade experiments are. Okay, so okay, so I'm going to come back to the single atom source that I mentioned at the beginning. This is something we're getting serious about doing. And so, again, to go over the protocol, we start with atoms in one hyperfine level, use a Rydberg excitation to transfer one atom to the other hyperfine level, and then apply a light force that ejects the n-1 atoms, leaving one atom behind. And this is really an important ability if we want to go to large numbers of sites for a potential quantum computer. Right now, with our 2 sites, we're running basically the limit of Poissonian loading, where about 30% of the time we have occupation of each of one of the 2 sites, and so 0.3 squared, about 10% of our shots of our experimental realizations do we actually have one atom in one site and one atom in the second site. Obviously, that's not going to work even for, well, you can grit your teeth and do it for 3 or 4, but beyond that is going to be very difficult. And so we need some way to reliably load atoms into these sites. And so if you want even 20 sites, then you need to have kind of 90% fidelity of single atom loading in order to get a net to kind of have 10% success at having all the sites occupied. Okay, so this protocol that I've mentioned a couple times now actually is fairly forgiving as far as the initial Poissonian distribution of the number of atoms in a site. So this is a calculation of the probability of ending up with one atom, assuming a Poisson distribution, initial Poisson distribution with the mean number of 0 to 10 atoms. And the point is that because the protocol is driving pi pulses, to first order, you're relatively insensitive to the area under the pulse. And so the square root of n enhancement or the square root of n dependence, it's not necessarily a nice feature for this particular application of collective quantum manipulation. But the square root of n is not that big of a problem because of the fact that you're running nearly pi pulses. And so if you assume 6 atoms or whatever with a Poisson distribution, you end up close to 90% kind of performances. And if you start with a large enough number, in principle, there's no bounds on the fidelity. Now, if you have some way of making an initial measurement at it doesn't have to necessarily be, well, you obviously need to make a sub-Poissonian measurement, initial measurement. You can improve on this quite substantially. Or if you have some other kind of filtering scheme, that might also improve as well. But the point I'm trying to make is that even this very simple protocol actually is fairly fairly promising in not being too stringent on this initial number distribution. Okay, so our first attempts to do this have involved our quantum computing experiment that Mark again will talk about tomorrow, where we have the atoms confined in a small enough volume that we have a blockade shift of 5 or so megahertz. And so we really have a situation where we think there should be good blockade of the whole sample. So the protocol, the experimental sequence is to load atoms. For the actual loading, we skip the atom number measurement, but we need to have an idea of what our number of atoms is. So sometimes we make an atom number measurement. We do optical pumping, then drive Rydberg pulse to put hopefully one atom up in the Rydberg state. We drive a pi pulse in the ground state to move the n-1 atoms to the other ground hyperfine level. And then we bring down the Rydberg atom and do another pi pulse and this last pi pulse is just to put our one atom in the state that doesn't get ejected and the n-1 atoms in the state that does. And so then we blow away the f equal 2 levels atoms, which are supposed to be the n-1, and then finally make an atom number measurement when we're done. And so so this is what we've done so far. We're starting with a mean number of about 6. And what we find when we do this is about 50% zeros and about 50% ones and very small fraction of 2s. So the fact that we're seeing very small fraction of 2s is confirming that our sample is well blockaded. Not yet sure exactly what's going on to keep this number from being, this number should have been in the 65 to 70% kind of range, given the fidelity of our single atom Rabi flopping. So this is very preliminary. This is literally taking a couple days of off from our other activities to try to do this. But it's very encouraging to be seeing this is highly sub-Poissonian atom loading. All right. So the point I've been trying to make here is to draw a clear distinction between the requirements for doing quantum manipulations and the requirements for other kinds of interesting experiments that have blockade ideas at their that depend on the blockade ideas. And so dephasing and suppression, these kind of effects are basically sensitive to the strongest interactions in the system, relatively insensitive to these weakly interacting states, which, however, dominate the possibility of quantum manipulation. And then I've showed you our first attempts at the deterministic single atom loading. So the four-wave mixing experiments are done by Jason Day and Eric Brecky and Lisa Hardy. And then the single atom loading is done in collaboration with Mark and these people here. Thank you.
Questions with that?
Concerning your single atom loading, as far as understood, one problem is that the pi pulse depends on the number of atoms in your well.
Right.
Can't you avoid it using a stirrup process, which shouldn't be insensitive to the number of atoms?
I think there's probably you can do some pulse shaping, stirrup kind of things, improve it. Absolutely. We're set up to do square pulses at the moment, and so that's what we've done. But yeah, I think that you could improve it substantially with that kind of those or stirrup or other related pulse shaping kind of tricks. Yeah, in a sense, this is kind of the hardest way to, probably the worst pulse sequence you could come up with, right? However, the easiest one to do in the lab.
I think that's your point, that is, even when the atoms are not interacting, you say blockade is still there. And why is that? I didn't understand.
I'm not sure. Could you repeat the question?
You say that even when the atoms are not interacting, the Rydberg atoms, even if they are not interacting, there is still a blockade effect. And where does that come from?
Okay, so I probably said that. What I meant was that if you want to have blockade over a certain distance, like we're kind of fixated on 10 microns, okay, the point I'm making is that for a blockade experiment, you have to have a strong interaction over that whole distance. However, for other kinds of experiments, you see the effects even though maybe the atoms are only strongly interacting over a 3 micron distance. So you can operate at, if you're at n equal 28 or whatever, the blockade interaction at 10 microns is completely negligible, less than a kilohertz. But if the atoms are 3 microns apart, they may have tens of megahertz of interaction. So you see dephasing, you see a suppression of excitation for quite low quantum numbers where you would not be able to do quantum manipulation.
Yeah, I think maybe what Bo is referring to was your comment earlier in your talk that the atoms feel no forces. I think what this means is that on the time scale of the experiment, they are interacting, but the forces are so weak that they aren't producing.
Well, if the blockade works, then there's then 2 atoms, you never get 2 Rydberg atoms, if the blockade works, okay? Now, obviously, there is some finite probability of double excitation, and so the actual force is the the force that you would have if they were fully occupied multiplied by the probability, something like that. But to the extent that it works well, you don't get any interatomic forces, and that's actually critical for the operation of this as a gate. Because if you have forces, then you're going to entangle the external degrees of freedom in with the internal degrees of freedom. And one of the really nice features of a blockade kind of mechanism is that you avoid having to control those external degrees of freedom.
In all cases, the interaction between the Rydberg atom with the ground state atom is not important.
That's extremely small on these scales. Until you get sub-micron kind of distances, that's much, much smaller than the Rydberg.
I haven't seen the effects of
No, but we'll hear all about it this afternoon.
Bob, did you have a question?
If there are no further questions, let us thank Tad and the rest of the students.
Thank you.